Hello, my name is Bob D. Hilster, and I am your particle model guru. Today we're going to be talking about the magnetic field around the electromagnet and the magnet. So far, I have actually done two videos on magnetics. The first one was the magnetic field, what is it, where I used a wire to describe how a magnetic field is developed. The second one I did was the Earth magnetic field and what the direction of the G1 particle is through the Earth and how it works with the compass. But today's video is on the electromagnet and the magnet. This was a screen out of a slide out of the first one. And this was the summary where you have a battery with G1 particles going from the positive end of the battery through the negative, and a current limiting resistor. And so the red shows the G1 particle flow. The black line shows the F2 force field that I assumed was true around the copper wire, and the resulting spiral type flow of the magnetic field around the magnet, around the wire, as opposed to just straight circles. Okay, and the second one, this is a slide from the one from the Earth, where it shows the F2 force field around the Earth, the G1 flow this way, coming in at the south pole of the Earth and out the north. And if you remember, the flow of the G1 particle through the compass inside the magnet is from the red to the white, or gray in this case. And again, we have an F2 force field built up because of the G1 flow. And so we're going to look at the electromagnet. This is a nice picture of a coil of wire, insulated wire, wrapped around an iron core. It's straight from Wikipedia. A couple of interesting slides here. Here's an electromagnet underneath a sheet of paper, and you can see the iron filings kind of glomp up here at one end, the other end indicating the field is very strong here and very strong here. And you can sort of see some lines. Not a very good picture, although you can't find many good pictures. And here's a second one where you have an iron nail wrapped in a wire with, and you can see again how there's a strong force here and a strong force here, and the path. It's not as well defined as a magnet, but nonetheless, it's there. So starting with that wire, one I did with the wire. In this case, we're just taking a loop. Now, granted, this is showing current, and therefore you use the right-hand rule. If you're going to show G1 particle flow, it's the opposite direction, you use the left-hand rule. Nonetheless, the field around the wire is the same. And so this is the same as the first video I had, only it's got a loop, and it shows you how the field would develop around one loop. But electromagnet is a composite of many of these loops. And again, the drawing is based on current instead of particle flow. But nonetheless, what you see here is around each wire is a magnetic field circulating around, just like and down here. Up at the top, it's counterclockwise. Down here, it's clockwise. They're opposite because the current is flowing into, or if it's flowing out of the paper here, it's flowing into the paper there. And so you have this one going counterclockwise and this one going clockwise. And what I mean by a composite field is when the G1 particle is moving at speed c, and these wires are all clumped real close together, there's a possibility, of course, that it instead of going circling around like these, it starts to circle as a composite signal. That is the general theory. This is nothing new here. This is the way you would see it explained in various links on the internet. Okay, so the question is, how does a G2 force field build up? And by the way, I'll be calling the G2, instead of using this on a diagram, for example, which I'll have later, I'll just use F2. F2 is the net G2 force field build up around any object based on the loss of the G2 particles as they go through the object. Okay, how does the G2 force field build up? And I just stated F2 is the net G2 force field around the object. Now we've had another experiment that I did a video on a double slit experiment with a detector. And if you remember, when the detector is turned on, you have lots of G1 particles flowing through the detector, and you end up with a strong F2 force. With the detector off, you don't have as many G1 particles. You do have the G1 orbitals. You have them, which is still going to set up a G2 force field, but so it's going to be a weak force. Same thing with the copper wire. With the DC current on in a copper wire, you get a strong F2 and a magnetic field. With no DC current, there's a weak field, but you don't detect a magnetic field, even because the force is too weak. So it's generally the F2 field is built up based on the particle density of the G1 particle inside the object. So I'm ahead of myself as usual. When there are many G1 particles flowing through an object, there's a strong G2 force field, F2, around that object. The direction of the F2 depends on the distribution of the G1 particles inside the object. If the object was spherical, that easily points to the center. As you'll see in the examples here, they're not necessarily spherical. Going back to this drawing, one could imagine that, at least as a cross-section, which this is, that the field, the high-density field, is actually rectangular, not spherical. But in any case, I'm going to make an initial assumption, a first guess, if you will, that the center of gravity of the G2 gravity of these G1 particles is right here in the geometrical center of the field inside and around the magnet. So I took a copy of that and I drew this messy drawing, but let me explain it as best I can. Here's a spot in the middle. That spot is representing the geometric center of this G1 field of particles. Then I drew a line. I drew a particle here, a particle there. I got particles all over in 5 different places. And I drew a straight line from this particle to the center. There's a very light pencil line. You might be able to see it, hopefully. And then I highlighted the F2 force, the net force. This net force is the difference between the number of G2 particles coming to this point versus the number of G2 particles here, indicating there are more G2 particles pushing on that G1 particle in this direction than there are pushing the opposite direction. So this is the G2 net force field is always referring to the excess number. So the force is generally in that direction. We're going to take a look at three of these a little bit closer. On the bottom right, we have this particular force field. This is the particle right here. You can see the arrow showing, and I'm assuming that for the purpose that the G1 particle is moving in the direction of that arrow, which says I clipped off the velocities. I write this is the velocity vector. This is the direction the particle would go if there were no F2 force field there. So but this force field could be broken up into its components. And the way you do that is you go to the end of the F2 vector and you draw a line perpendicular to the velocity. And then you go from the tip of this one and you draw a vector in line with the velocity, perpendicular to the velocity, in line with the velocity. When you sum these two vectors, you get that vector. So these two components of this vector add up to the same thing. The one that's perpendicular is going to push or turn. It's going to turn the particle. The one that's in line with it is either going to speed it up or slow it down or do nothing if there is no vector in that direction. So this particle wants to go out here, but this force is going to push it this way. And you can take this little triangle all the way down to here. The particle wants to go from here to here, but the force vector perpendicular to that's going to push it this way. Going to push the particle in that direction. Now the velocity vector is downward and to the right, but the force vector is upward and to the left. It's going to slow that particle down. In this particular case, as the particle is coming out of the electromagnet, the particle is slowing down. By the way, this force, which is the very strong force, because it has one of the longer distances, is also slowing the particle down, but it's not going to move it up or down because there is no vertical component. On the upper left, we have the opposite. We have the particle coming into the electromagnet. This is the force vector pointing towards the geometric center of the G1 particle field. That vector can be broken into two components, one perpendicular to the velocity, one in line with the velocity. And so what this particle wants to do here is it wants to continue going out this way. It wants to go in a straight line, but this force vector is going to push it up. It's going to, instead of going straight down here, it's going to be pushed up and more likely follow that line. In this case, the vector in line with the velocity is in the same direction as the velocity, and this particle is going to speed up. It's going to go faster. And the third one I'm going to show you is one right at the top center. The particle wants to go this way. It's going to be pushed down. It's already perpendicular to the velocity vector. So there is no horizontal component of the F2 force, and therefore at this point the force is neither speeding it up or slowing it down. It'll maintain its velocity, but this will push it down. The particle wants to go out here, for example, but the force pushes it down. So you can see in general that how these forces, there's one here that I didn't show. There's one here that I didn't show. But you can see how these forces would, in fact, at least conceptually, cause the particles to do this. One of the real interesting points, and I think I'm getting ahead of myself, but I'll do it anyway. This force is very strong, which not only means is the particle is moving very fast, going in just going faster and faster. When it comes out, it goes slower and slower because this force is pushing it backward. It's going slower until it reaches this little. I'll put a little line here. So it's going to slow down until it reaches here, but from here to here it speeds up. From here to here it slows down, speeds up, slows down, speeds up, slows down. And since this is I'm treating this as a gravitational type force, you can, if you ever study the velocity of the moon around the Earth, you'll find that it speeds up and slows down the same way. Okay, so let's go on to the next one. No, this is the magnet. I'm not going to go through the whole thing again. This is just a artist's conception of a magnet, and you can imagine if I were to let this point in the center be at the geometrical center be the direction in which all the F2 forces point, I'm going to get the same result, whether it's a magnet or an electromagnet. And the strength of the force varies basically on the distance it travels. I said earlier, this is the one here the force going in here and the force pushing back here are very strong because the G2 particle from this end has to pass through all of that before it gets here, and here it does not. So there's a strong force. Vertically, this force is not, I would expect this vertical force here pushing up or pushing down to be weaker based on just this distance. Ironically, the strongest distance ought to be the diagonal one. That's what you would guess. Can't say that that's what I believe is absolutely true, but that's what you might guess based on this analysis. So we conclude that the main feature, not the only one, but the main feature that controls the path of the magnetic field is primarily based on G1 particle density of the object, even though there may be other factors, for example, the prism, the direction of the force, the F2 force in the prism is perpendicular surface, not towards the center. So there's other factors that can get in there, and I have no way of knowing whether that applies to the electromagnet or the magnet. The speed of the G1 particle around and through the magnet and the electromagnet is not constant. The G2 force field is basically speeding it up or slowing it down as it goes around. And since light is a stream of G1 particles with a repetitive pattern, I've talked about that before, the speed of light is not constant. I had a video titled Faster Than Light. Drag, what I talked about in that video is that drag can slow it down, and drag is nothing more than the G2 force field that opposes the velocity of the G1 particle. That's the conclusion. Anyway, my name is Bob D. Hilster, and I am your particle model guru. Tune in next time when I explain more of the universe using the particle model. Thank you for your attention.